Today we're going to talk about PageRank, and you're going to see lots of stuff on PageRank. This was a key invention that led to the founding of Google in the early 90s. And I'm going to give you some mathematical foundations. I'm also going to talk about extensions, like what's called topic-specific PageRank or SimRanks for finding similar pages, TrustRank, and I will explain how web spamming works, how that search engine optimized companies can try to increase the rank. So there's a continuing battle between search engines and these guys. Okay? Let me first start. Let me give several definitions of PageRank. I'm going to start with fluid. So there's going to be, in this course, both intuition and mathematics. A lot of intuition, a lot of mathematics too, some. And I'll give multiple ways: a fluid algorithm, random walk, and matrix representation, all for the same algorithm. And then I give you some intuition on matrices and eigenvectors, eigenvalues, which maybe you've seen. Hopefully you get good intuition here. Okay. So in a PageRank, there's only one value for each web page. So it's a big directed graph on all the web pages. And each page has a value that is computed. And the intuition is a page that is important is pointed to by important pages. And an important page points to important pages. So that's recursive. That means there's a recursive iterative algorithm. First intuition is that it's kind of like a liquid, fluid. Each web page or node is a container, and the links are pipes. And you start by putting a little bit of fluid in each of the web pages. And then the fluid will circulate according to some rules. So if you have 1 liter, then 1 over n liters is put in every page. And then you repeat. So there's a link from P to P prime. So each page P has links going out. And if there's n links going out, maybe there's only 3 links going out, each link will get 1/3 of the fluid. So the fluid is divided between outgoing links. And then in the next step, you look at the links coming in, and for each incoming link, you take the fluid. So you see the fluid circulates like that. And eventually, it converges. So here's an example of web pages. So there's 8 pages here. A, B, C, D, E, F, G, H. Each page has 1/8. So now the fluid circulates. And how does it work? Well, look at page A. So page A has D going in, E going in, H going in, F going in, and G going in. And so what happens is, after one iteration, A has 1/8 liter, which leaves, and all the in-links, the fluid comes in. So D has 1/8 liter, but has 2 outgoing links. So it's divided 1/2, so you have 1/16 coming from D. E has also 2 outgoing links, so there's 1/16 coming from E. H has no outgoing links, so everything goes there, so this is 1/8. That's H. F has no outgoing links, and G neither, so there's both 1/8 there. That's F and G. So the total is 3/8, 4/8 is 1/2. That's after one iteration. And you do the same for all of them, and you keep going until it converges. And you can prove it converges, which we will do in a little bit. And after you keep doing that, you get these numbers. Okay, so A has 4/13, B has 2/13, D has 1/13, and so on. So this is the result of the PageRank. It's just this fixed point. So A is the most important page here, and D, H, E, F, and G are less important. Okay, so that's the basic idea. Of course, there's a problem. It's not going to work if you do like that. So this basic algorithm is nice, but it doesn't always work, so we have to fix it. So let's say we change the graph. F points to G and G points to F. They don't point to A, they point to each other. So what happens now? The thing keeps circulating, but look, all the fluid that comes in here never goes out. You see that? When it just will accumulate here. All the fluid eventually, this part will empty, 0. Everything will eventually come here. F and G will each get a half. Everybody else gets 0. That's not good, huh? So you think, well, this is a stupid algorithm. It's very bad. Well, the insight from the smart guys who made Google is we can actually fix this problem. So you see the problem, huh? You can still use the fluid intuition to fix it. Look at the Earth. Water flows down, right? Rivers, everything goes into the ocean. But why does not everything stay in the ocean? Still there's water on the mountains, because there's water also going up. This is going up by evaporation. So it's kind of circulating. So you have lakes in the mountains. And that's what they do now for the PageRank algorithm. You can, the update rule. So it's not just what fluid going in, there's also fluid going out. So you take the fluid, okay, so you make a scale. At the end of the day, you reduce the fluid in each page by some factor S, like 0.9 or something, and you add a little bit of fluid, 1 minus S over N, everywhere. So even the pages very low PageRank will get some. So it's like a random jump, okay? So basically the PageRank evaporates from each node and it rains uniformly on all nodes. So that means we have now a cycle between all nodes, and this fixes the problem, okay? Okay, so you have the basic update rule extended with scaling. So this is the evaporation. You can show it converges, which we will show in a little while. It's matrix computation, which we'll show later. And the real scaling factor is some number very close to 1, 0.8, 0.9. So that means most of the time the fluid stays on the page, but a small percentage of the time it jumps and evaporates. Okay? And this definition, the fluid definition, is equivalent. You can say it's also kind of, you can formulate it as a random walk definition. This is maybe more intuitive for humans. Let's say you have somebody who is browsing the web randomly. I'm looking at a web page, and then I click on the web page, so I jump from one page to the other, and I keep clicking, so I'm surfing for K steps, and then I get bored and I look at another page. So it's like I'm walking randomly on the network, okay? And you walk K steps, and then you jump to some random page, you walk K steps, then you walk, jump, and you walk K steps. So this is, the walking is exactly the PageRank after K iterations, and the jump is the raining with the jumping to random page with probability 1 minus S. Okay, so it turns out they're equivalent, which we will see in 2 minutes. Okay, so this is the basic algorithm. It was modified a lot. Okay, so So I won't say so much here because we're going to go into the other slides. Search companies will cheat. They don't call it cheating. They call it search engine optimization, please, SEO. And if I want to be very high on the Google ranking, I pay SEO companies some money, and they will do some magic, and all of a sudden I get very high scores. And it works using something called link farms, which we will explain. Okay, and also something we mentioned before is advertising. So it's the links. You also have paid links, and Google makes huge amounts of money with that. Okay, so that's an extension. Okay, so let me now go to the more in detailed discussion of PageRank. So these slides are actually by a colleague of mine called Sarunas Girdzijauskas, who is, I think, from Lithuania, but he's now in Sweden, KTH. So he was very nice. He gave me these slides, which I modified a little. So this goes into a lot of detail, okay, on different kind of things for PageRank. So first, I want to give you intuition. We will go a little bit into the math, matrix, representation for random walks, the notion of eigenvalues. Then I will show the PageRank algorithm, how it works exactly, formally. And then we go beyond PageRank. How can you search in a more focused way, topic specific, or how you can find similar pages using variation. Let's say I'm looking for movies that are like this movie, okay? So, for example, I liked a lot the movie Dune, and I want to find movies that are like this movie, so SimRank lets me do that, so it's similar. And the final thing is I want to explain how the cheaters work. So this is called web spamming. So very quickly, after Google invented the PageRank, the companies invented the ways to cheat, okay? And this is called link farming. So I'll show you exactly how it works. And we'll figure out how can you increase the PageRank artificially. And then I'll show you some algorithm called TrustRank to go bypass the cheaters. Okay. So the first part of the talk is more general talk about random walks and matrices. So this gives you kind of intuition on the mathematics. So I'm going to give you mathematics, but also intuition. So the first thing I want to talk about is random walks. So here's a graph with vertices, 1, 2, 3, 4, 5, and edges connecting them. And I want to do a random walk. That means I start somewhere. I've got node 1. I move to a neighboring node with some probability. 1 over d of v. So d is the degree of the vertex. It's how many links there are. So the node 1 has a degree of 2. So there's 1/2 probability of going on each of those links. And then I keep making walk steps. And the sequence of this technically is something called a Markov chain. I'm not going to give you so much theory, but it's basically a sequence where each step is chosen according to some probability, and there's no memory. I mean, it doesn't remember where it comes from. You just, each step, it's there, it makes another jump, but it actually has no memory where it came from. So that's called Markov chain. Okay? So let's say we start at node 1. So here I make a table. So node 1, here. So at the beginning, at time 0, I have 1 probability of being at node 1 and 0 for being everywhere else. And then I do 1 step, a 2-step, 3-step. And each step I will do random. I will walk randomly according to the links. Okay? So after 1 step, see how it works. I will be either at node 2 or 3 with probability 50%. Okay? And then I keep going. So the 2 can go either to 1 or 4, and the 3 can go to 1, 4, or 5. So the 0.5 will be split between 1 and 4. And the node 3, the 50% will be split between 1, 4, and 5. So 16% or 17 for each of them. So that gives me this. That means there's a 42% chance of being in node 1. So where does this number come from? Well, it means I have a 25% chance coming from node 2, and a 17% chance of coming from node 3, and 25 plus 17 is 42. That's very interesting, huh? Also being in node 4, I have a 42%. And node 5, there's only one way to get there. It's from 3 because I'm not yet at 4. So there's a 1 over 6, so 17%, rounded to 2 decimals. And the sum of all these is normally going to be 1. Might be slightly different because of round-off error, but it's supposed to be 1, okay? So I keep going. You can see now the numbers change. After 3 steps, I will be in these places with these probabilities. And I keep going, and I can keep going. 4, 5, 6. And you see, eventually, it's like they're kind of converging, okay, to some value, okay? And it will converge. So the initial node, I started with node 1, but of course you can start with more nodes. So here's a longer table. So you start from 0 up at the top, and you keep going. And it kind of looks like it's converging, right? 17, 17, 25, 25, 17. What do you think? Seems to be, smells like it's converging up. And it does actually converge. And you can prove for any connected, non-bipart, bidirectional graph at any starting point, the random walk converges. And now I want you to have intuition on this. The graph has to be connected, of course. If it's not connected, if it looks like this, so let's say the graph looks like this, and there's 2 pieces. Well, if I start here, I will never get there, okay? For example, or if I have a bipartite graph, see, depending on if I start here or if I start here, I will converge differently. So it's not really converging for any random starting point. See, here I say any starting point. So if the graph is not connected, then the convergence would be different depending on the starting point, right? So it has to be connected. So you have to understand, intuition is important. It has to be connected. It has to be non-bipartite, because if it's bipartite, then you can divide the graph into 2 pieces. If I start here, then I will go here, and it will be oscillating forever. All the probability will be here, and this will be 0, and then it will all be here, and all this one will be 0. So it's oscillating and not converging. So that's why it has to be non-bipartite. You see that? So you have to understand this intuition, So it's not just random words there, okay? So you make sure you understand, okay? And the unique, there's only one result. Unique stationary. Stationary means that once you converge, it never changes anymore, okay? So this is a kind of iteration, which we call power iteration, okay? So this is the final value, 17, 17, 25, 25, 17. What do those numbers mean, actually? Actually, we can figure it out, what they have to mean. We can actually give a formula for this. The random walk, so pi is the final set of probabilities, and it's stationary, so it's staying the same. D of V is the degree, and M is the number of edges, okay, in the graph. So in this graph, 1, 2, 3, 4, 5, 6 edges. So 2M is 12. So 3 is the degree 3. 1, 2, 3. And 3 divided by 12 is 1/4. 25%. That's a coincidence, huh? 2 has 2 outgoing edges. 2 divided by 12 is 1/6, which is 0.17. Amazing, huh? Isn't it? But we can prove that this has to be the right value. It's actually very easy to prove. Okay? We can prove that this value is a fixed point. That means if you do one more iteration on this value, you get the same value. So we start with pi, and we will do one iteration giving pi prime. Okay, and so how do you do that? Well, the new value is all the ingoing links. Okay, so for node V, we take all the links going from U to V, and for each one of those, we have the probability on U divided by the degree, 1 over D. Okay, this one is du over 2m, and the du's cancel, so we get the sum of 1 over 2m, the links coming from U to V. But how many links are there going from U to V? Well, it's exactly the degree of V. How many links are going to this node? 1, 2, 3, okay? That means it's the degree of V divided by 2m. Pi prime is equal to pi. So you can show that it's the degree divided by 2n. Right? Neat, huh? Now, there's another thing. If the graph is D-regular, so D-regular means that all the nodes have the same degree D, everywhere. If it's like that, of course, then the probability is going to be the same everywhere, huh? So uniform means it's the same. So if I have 3 links on every node, it's going to be the same, uniform. Okay, that's intuitive, right? So you have to get the intuition. Okay, so this is just some numbers showing how it works. So the stationary distribution is proportional to the degree of V. Degree is how many links. Okay, so what does that mean? There's intuition. Well, it's pretty clear. The more neighbors you have, the more chance that people are going to come visit you, so the probability is higher. See, that's kind of the intuition. Okay, so you can see how the matrix, the random walk is going to work. Now let's look at a more numerical, formal representation, a matrix representation. We're going to do the same thing now with matrices. So here is my graph, so I'm going to keep using the same example. And there, that matrix called A is the adjacency matrix for this graph. What does it mean? Well, if you look at the rows, there's 5 rows and 5 columns. So if there's a link from 1 to 2, that means there's a 1 in element 1, 2. So the first row, second column. So that means so this link, 1, 2, means that there's from row 1, there's a link to 2 here. There's also a link from 1 to 3. So row 1, column 3, is a link here. And each row corresponds to one node, the origin, and the column corresponds to the destination. Okay. So how many ones are there in that graph, in this matrix? How many ones? You have 1, 2, 3, 4, 5, 6. 6 edges, huh? So how many ones are going to be in there? 2 times, because of course they go both directions. 1 to 2, 2 to 1. So you'll have 12 there, huh? See, it's very intuitive, huh? So that's the first matrix. It's called adjacency matrix. But now we want another matrix. because we're going with probabilities. We have a probability, so we want that to be in the matrix too. So first I want to define a special matrix called a diagonal matrix D, and each value on the diagonal is 1 over the degree. So for the first element it's 1 over 2, then 1 over 2. Node 3 has 3 links, so it's 1 over 3. Node 4 has 3 links, so it's 1 over 3. And node 5 has 2 links, so it's 1 over 2. So why am I introducing this matrix? Because it lets me define another matrix, which is called the transition matrix. So this one is actually D times A. So what does it mean? Instead of ones, I now have probabilities. So if I'm in row 1, if I'm in node 1, there's 1/2 probability I go to 2, and 1/2 probability I go to 3. You see that? So in each row, all the elements tell me the probability they go to the other one. Question?
Yes. In PageRank, we have a directed graph, correct?
Yes, we will get to that.
Okay.
So yes, I'm talking now undirected graph, but we will get to directed graph, and you'll see what happens when we get there. It's very interesting stuff, but you have to understand first this piece, this one, huh? Yeah. No problem. We get there, and you will see all the neat intuition that comes when the graph becomes directed. So here, I'm just giving you intuitions, okay? Because eventually we're going to be talking PageRank, and then I want you to understand that stuff, okay? So if you're in row 2, you can go to row called node 1 with probability half, and node 4 with probability half, huh? If you're in 2, you go to 1 or 4, huh? See how it works, huh? So all the ones in a row are turned into probabilities, so the sum of the probabilities for each row is equal to 1, huh? And this matrix is actually D times A. So there's 2 matrices that are really important here. The adjacency, which gives you the graph, and the transition matrix, which gives you the probabilities. Okay? So formally, A is n by n adjacency matrix of the graph. Aij is 1 if there's a link between nodes I and j, and otherwise it's 0. Okay? Actually, you can say it gives me all the paths that you can do in one hop, because you're making one connection, okay, in the adjacency matrix. Now, let's go do a little bit more intuition, and I'll show you, and you'll see how neat the matrix representation is. Let's say I want to count 2 hop paths. I want to go 1, 2. How many are there? From a node, I want to go 2 hops instead of 1. You know, it's so neat. It's just A squared when you do matrix multiplication. The A times A, the matrix multiplication, gives me the number of 2 hop paths. Okay? And A cubed, what does A cubed give us? Well, the number of 3 hop paths. Okay? So how does that work? Well, I'll give you some intuition. Okay, a small technical thing. It's actually giving me walks. Sorry, I have to be technical about graphs. A path is when you don't repeat any vertices, so it's like a marking on the street. Whereas a walk is like a person walking back and forth, so you can actually repeat vertices. Okay? So actually we're counting walks. Okay? To be very technical, we're counting walks. Okay? So how does it work? Actually, you should make a diagram and figure and understand why the matrix multiplication gives you that. Okay? So let's say I want to do A times A. Okay, A times A. And here I have a row here I have a column J. Okay. So, and here I have ones and zeros. For example, some way, and this will give me element ij. So how does it work? So these are, the one means you have one hop, from I to 1 to etc. So how does the multiplication work? 1 times 0 plus 0 times 1 plus 1 times 0 plus 1 times 1. Well, how does it, what does that mean in terms of hops? Here I'm going from I to 1. And here I'm going from 1 to j. You see that? So I go from I to 1 and then from 1 to j. Then I go from I to 2 and from 2 to j. From I to n to j. So each one of these combinations is going from I to j, but the node in the middle is different. You see that? And it's only going to be 1 if there's both 1s. That means if I have a path from I to 2 and 2 to j, it's going to multiply 1 times 1. So it's only 1 it's if the number, if there's actually a path there, or a walk. So if you sum them all, it gives me all the possible walks from I to j with 2 hops. Okay? And if here, and it keeps going like that, if you put a matrix here which gives you n hops, then here you will add 1 more, and you get n plus 1. Do you see how it works? So matrix multiplication gives you the total number of walks. Okay? So what if you take the vector now, 1, 0, 0, 0, 0, and you multiply by a? Well, it's like you start. Okay? You're starting from 1, or 0, or 0, or 0, or 0. So the number of walks, the one where you start from is 1, 0, 0, 0, 0, is given by that. So basically it tells you how many walks of length 1 that start from node 1 ending in node I. Okay? And you could do multiplication for that. See how matrix multiplication is really neat, So VA squared, it gives you 2, 0, 0, 2, 1. So now we have 2 walks going from node 1 ending up in node 1, or 2 walks from node 1 ending up in node 4. Okay? See, that's neat, And 3 gives you how many walks of length? 3. And it's all the same. I'm always talking about this one. So you can see how the matrix really corresponds very nicely to graphs and doing things on graphs. Okay? Okay, so far we did the adjacency matrix. What about the random walk matrix, the transition matrix? That's this one, M, with the probabilities. Okay? So this gives you the probability of ending up somewhere. Okay? If you start in node 1, the probability of ending in here is 1/2. Probability of here, the probability of ending in node 4 is 0. And you can do squares. So for example, if you keep going, if you take this vector here and multiply again by m, the number you get here is actually the probability that you end up in those nodes when you start with node 1. It's neat, huh? Question? No? It's okay? So you can see how matrices and graphs are very close. So this is going to help us understand PageRank, yeah? Okay. So we have a random walk on a graph G. Now we start doing random walks, like PageRank. We start at node V0, and after t steps, we end up in node Vt. We move to a neighbor with probability 1 over the degree. Each time we go to a node, if there's multiple paths, we divide evenly. And the chain of random nodes, it's what's called a Markov chain. So a Markov chain is a sequence where whenever you make one step, you make kind of a random choice, some probabilities, but you forget everything you did before. It only depends where you are now, so there's no memory. Okay? So the initial state would be here, so you have probability 1 of being in node 1, okay? Now, you can do multiple steps. So after t steps, the probabilities is given by this vector, pt. P0 times m power t. So this is matrix exponential, matrix multiplications. See how it works? If you're a stickler for putting the m on the left, you have to do transpose, of course, because you have row vectors here, but that's a detail. Okay. So here we have pt is p0 times m to the t, and we start again with our matrix, and we start with the 1, 0, 0, 0, 0, and we do one step. So we have probabilities a half and a half for getting there, okay? And then we do again, and we keep going. And eventually, it's going to converge. Remember, I showed you the table. We're doing the same thing here. So when pt plus 1 is equal to pt, we have reached the stationary distribution. So let me call this vector pi. Okay, it's not 3.14. It's not. I have not chosen this notation, but this is what Sarunas has chosen. So pi times m is equal to pi. Stationary. If we start with these probabilities, we make a step, we end up with the same probabilities. Okay? See that? You remember the notion of eigenvectors? Have you seen that? Well, this is an eigenvector here, yeah? Remember? Every matrices have special vectors called eigenvectors that give some property in the matrix. So V is an eigenvector of M, and lambda is the eigenvalue if V times M is equal to lambda, which is a scalar number, times V. It's just it's scaling the V. So this one is clearly an eigenvector, right? Interesting, huh? So PageRank is connected to eigenvectors. Pi is an eigenvector of M with eigenvalue lambda equal 1. Okay? Okay, so that's the first part. Let me go on now. Let me go on now by giving you some more intuition on eigenvectors and eigenvalues in terms of graphs. So eigenvectors and eigenvalues are very useful things, but with graphs they have some really neat properties. So remember this. Okay, this is what we just saw. We have pi is an eigenvector with eigenvalue 1. But we can actually say more things. Okay? There's something called the spectrum of a matrix. I'm not sure if you saw that. Have you seen that? Have you seen that spectrum? Yes? Good. That means this will be very easy, right? No? So assume now I'm going to give you some intuition. Assume you have a D-regular graph. So that's a graph where all the nodes have degree D. So they're all 3 links coming out, for example. Right? Okay. And now we have A, which is the adjacency matrix for this. So A times X. Okay. So this is just a matrix multiplication. A times vector X equal vector y. Okay. And an eigenvector, this is a refresher, an eigenvector is a vector x such that this is equal to some number times that. Okay. So what happens with degree d? Now we're going to connect the eigenvalues, eigenvectors with graphs. Okay, graphs, which are these visual topological things, like on the web, and matrices, which is just a bunch of numbers. How does it connect? Suppose all the nodes have degree d, and g is connected. So it's a d-regular graph. Huh? Okay. What are some eigenvalues? Well, let's try. Let's say we try the vector 1, 1, 1, 1 only once. This graph. Okay? Then a times x will be d, d, all the d's. Because each node has 3 outgoing links, but also 3 incoming links. So the number of ways of going into a node is d. So that means d is an eigenvalue. So if you have a graph with only degree d, well, d is an eigenvalue. So eigenvalue is somehow connected with the degree of the graph. It's funny, huh? Interesting, huh? Okay. So the vector all ones has an eigenvalue of d. Okay. This is actually what's called the principal eigenvector. But let's look at some other graphs. So the d-regular graph is like a very simple, uniform graph. Let's look at some other ones. Very interesting. Okay, in general. Now, there's a concept called spectrum of a graph. So if we have now a matrix A, adjacency represents the graph. V times A is equal to lambda times V. Well, if it's a column vector, you can say AV is lambda V. Yeah? Here we have row vectors. So if A is a real symmetric matrix, so for non-directed graphs it's symmetric, real numbers, then it has n eigenvectors and n eigenvalues. And all the eigenvalues are real numbers, and you can order them, lambda 1, lambda 2, up to lambda n. That's something you can show. And the eigenvectors are orthogonal, so they're orthogonal to each other. And if G is a D-regular graph, then lambda 1 is equal to D. Somehow, degree of the graph is connected to the eigenvalue. Okay? For a random walk matrix, which is not the degree D, which is a random walk matrix, you have normalized. This is the one where you have probabilities. The principal eigenvalue is 1. Okay, here you have probabilities. It's not the adjacency. Yeah? It's the probabilities. The eigenvalue is 1. Okay? Okay, this I will skip. There's another concept called graph Laplacian, but we're not using it. But Sarunas wants to tell you about it, but I'm not going to tell you about it. And the set of all the eigenvalues is called the spectrum of the graph. Okay? And this could be for the A, the adjacency, or the transition, the probability matrix M, or the L matrix, which I'm not talking about. And there's a very interesting number called the difference between lambda 1 and lambda 2. So lambda 1 is the principal eigenvalue, but lambda 2 is also interesting. And there's a number, lambda 1 minus lambda 2, which has a name, which is called the eigengap, or the spectral gap. Okay? And for n, it's 1 minus lambda 2, because lambda 1 is equal to 1. Okay? Fine. What if the graph is disconnected? Okay, now we're going to show some examples to make work your intuition, and that will all help for later when we start thinking of the PageRank, okay? What happens if the graph is disconnected? Well, lambda 1 is equal to lambda 2. That's weird. If the graph is disconnected, you could actually say something about these two highest eigenvalues. Okay? So let's see how it works. So now I'm going to give you some intuition. So let's say we have a graph that's not connected. Two components. Each one is d-regular, just for simplicity. So each one has the same number of links. So we could have two little triangles. So what are some eigenvalues for this? Well, for example, if you put 1s on the A and 0s on the B, then you get a vector, right? 1, 1, 1, 0, 0, 0. Or you can put 1s on the B and 0s on the A, right? So if you put 1s on the A and 0s on the B, and you multiply by A times x prime here, you add up all the degrees. So you get d with zeros. So that means d is an eigenvalue. But you also have another vector, orthogonal, 0s and 1s on the B, and it also gives d. So you have two separate eigenvalues that are the same. Okay. Notice if the degree would be different for B, we would have different value. We could have d1 and d2. But here you have d for both, so they're the same. And you can kind of do approximation now. So we showed that if you have this, the eigenvalues are the same. You have two eigenvalues that are the same. Now assume that it's almost disconnected. You only have a small number of links here. Well, it turns out lambda 1 and lambda 2 will be very close to each other. It will be approximately 0. So you can see that the connectedness is somehow related to the eigenvalues. Okay? Okay. For every connected, non-bipartite, undirected graph, distribution converges to a limit. Okay? A unique stationary distribution pi. And if it's regular, it's uniform. Okay? Why connected? I mentioned already, yeah? The graph has to be connected. What happens if it's not connected? What happens if it's not connected? You see, I explained it already. It means that you don't have one unique stationary distribution then. You can have one or another one. Okay? What if it's bipartite? Then you will have all the probabilities on one side, so you can divide the graph into two sides. All the probabilities on one side are non-zero, the other side is zeros, and if you do one step, it all shifts to the other side, and you have oscillation. There's no convergence. Okay? And what about directed graphs? And now we've got to start going to directed graphs. So now you have already some intuition. What about directed graphs? Okay? So here's a directed graph. It turns out the directed graph has to be strongly connected. Remember, we said what it means, huh? That means there is a direct path from any node to another. What happens if it's not strongly connected? Oh, you have to have intuition there. We saw an example of that, huh? In the beginning. If it's not strongly connected, then they say walks will leak. It means that if it's not strongly connected, what happens? Okay, so that's one thing. Here's another one. Notice this one, this graph here. So this one on the left is strongly connected, so we're good. The right one is also strongly connected. No, this one is not strong, but this one has another problem. It's not you have actually two cycles going like this, okay? And this is a property called periodicity. The graph has to be aperiodic. So this is kind of generalizing bipartite. Visits to some node should never be a multiple of some number. So here, visits will be multiple of 3 steps, always. Well, if you do that, the whole thing's going to oscillate, okay? So if you do that, the whole thing will oscillate, and so it's not going to be convergent. So it has to be aperiodic. You're not allowed to have that. Okay? So the greatest common divisor of the lengths of all the cycles is 1. So you can see some intuition here about the graph. Okay, so all of that was kind of preliminary stuff to get your neurons moving. And now we can start talking about PageRank. Okay, so now I'm going to talk about Google PageRank. So first, I will give you a little history of web search. So this all started a long time ago in prehistory, another millennium, 1989, okay, which is a long time ago. It's really super long ago. It's like before Christ was born or something. So here you have the first generation of search. So you have people are making web pages, and people want to search them. The first generation was manual curation. So Yahoo, which started back in those days, there was little gnomes or monks sat in an office looking at all the web pages and kind of making directories. And I want science, I click on science, astronomy, okay? Yeah, but that's kind of not scalable, okay? So then now we have second generation, and there was a very nice one called Alta Vista, which you have probably never used, which I used. And this was classical information retrieval. So basically they look at the text in the pages. If there's lots of words on astronomy, then it's based on, then it's astronomy, okay? And they make indices. But this didn't work very well. And it was spammed. People did something called term spam. It was very easy to cheat from this. And then the third generation came, and they basically took over. This was Google PageRank. Okay, so this is the short history of web search. Okay? So what I'm going to do now is I'm going to explain Google PageRank, and we're going to use all our intuition on graphs and matrices and all that stuff to really see how to design it and how to make it work. Okay? But I notice it's 3 o'clock, so we make a break first. Okay. To design PageRank, and we're going to use some of the intuitions we saw before the break. Okay. So we have a bunch of pages, and here we're talking about votes. So it's like a fluid, but you have votes, and you distribute the votes to outgoing links. Okay. So if a page J has some votes, Rj, and n outlink, each link gets Rj over n. Okay, so that's clear. And so pages will vote. So the idea is that the more votes you get, the more important you are. It's like in an election. And if your page is important, then you have more votes, Rj is more. So a vote from an important page is more. So that's like what we saw before. Okay? And the importance of a page is the sum of the votes, the inlinks, so the other pages that vote for it. Okay, so this is something we saw, kind of. Okay, this is actually very similar to random walk. So we can actually say that Google PageRank is the principal eigenvector of the transition matrix of the web graph. Okay? So you have the web graph, which is huge, billions of links. So the matrices are very big. Okay? So we're going to compute this. We're going to compute the eigenvector of a matrix which is 10 billion by 10 billion on the side. That makes how many elements inside that matrix? Well, 10 to the 20th elements in there. So that's a lot, right? So can you see any issues with that? Well, I mean, not so many computers can store 10 to the 20, okay? That's one issue. But there's more issues. So we're trying to make it practical now, huh? So one issue is the matrix is huge. The other issue is, well, remember this diagram? This is the structure of the web. Well, in order for there to be a unique stationary distribution, it has to be a strongly connected component. So is this thing a strongly connected component? No. I mean, there's one inside, but it's not. So that's a problem. Okay, that's another problem. It's not strongly connected. So it's a directional graph. So here, for example, so there's two problems. So the Google people have some very nice terminology for this. So here you have a node which only has in links and no out links. So this one is called a dead end. Dead end. And we saw it already before the break. So you can say the votes leak out. Everything collects there, and they're not circulating anymore. That's one problem. Or another issue. So here's another graph. So this graph has a problem too. Can you see what the problem is here? So here you have 3 nodes. So the Google people call this a spider trap. Something that traps spiders. Not sure why they call it a spider trap, but it's called a spider trap. That's another problem. So the votes disappear. They all collect there. They're no longer circulating. And of course, it's not strongly connected. So again, these are all problems we have to fix. Okay? So how do we fix it? Well, we have to fix the graph. We have to make it strongly connected and aperiodic. Those were the 2 conditions. Strongly connected and aperiodic. And the solution of Google, okay, this is very similar to the evaporation idea, is you make very, very small links from every node to every other node. So this is the evaporation. That means there's a small probability of jumping from any node to any other node, but the main graph is still the same. Okay? So here's your main graph. Then you have another graph with very tiny, tiny probabilities, but between every node and every node, these are very tiny, and you basically sum them together. Okay? So you have a very nice animation, and it turns into that. Okay? So the idea is that you have a random walk, and when you're at a node, you will either follow the link or you will jump. So it's basically the evaporation idea. Some probability here, you call it beta. You follow the real link, and with 1 minus beta, you just jump to some random page. Okay? And usually, it's very close to 1. That means most of the time, you keep following links, but once every 5 or 10 links, you jump. So it's like you walk for 5 steps and then you jump. So if you're in a spider trap, going in a circle, after 5 to 10 steps, you will jump out of the spider trap. Okay? And if you go to a dead end, once you're in the dead end, there's no way of getting out, so you will immediately jump out. So dead end is a little bit special because there's no link going out. So the only way to get out is to teleport. Okay? So if you're a dead end, you're always going to teleport. So here's my graph. So here's my transition matrix for this graph. But this graph has maybe problems, we don't know. Maybe it has spider traps, dead ends. So we have another graph with very small values. Okay, here they're not so small because you only have 5 nodes. But if I have 10 billion nodes, the value of each one of these numbers will be like 1 over 10 billion, okay? So this is what we call the teleportation matrix. So you will combine these two matrices to get a new transition matrix, okay? Combine them, so you make the sum of them. So this one is the matrix that you will do with probability beta. So this is the step. And the teleportation you will do with 1 minus beta. Okay, and then you combine them. Notice you combine them. So this one is beta times this one, plus 1 minus beta times this, except here you have 1, and not 1 minus beta. Well, that's because it's a dead end. You can't get out here. Here, there's nothing here. So that means for the dead ends, you have to have an immediate teleport. Okay? There you have to have an immediate teleport. So you have 1 minus beta if these are not all zeros. But if it's a 0, you have to get out of probability 1. Okay? So that gives me this matrix here. Notice this one, second row, here it's zeros. That means you don't get out. Okay, once you're there, you're stuck. But you have to give it probabilities that add to 1. Okay, so that means you have to multiply this teleportation matrix by 1. So that gives you 1/4 probability of going to any other node. Okay? Okay, fine. Is it fixed? Well, if beta is 0, it doesn't work, but we assume beta is never going to be 0. But there's still other problems to make it really work. Okay, so you have this huge matrix. How does the matrix, the PageRank matrix, look if you have 10 billion pages? It's pretty big, dense matrix. All the elements are basically non-zero. Most of them are non-zero. N squared non-zero elements. That's a lot. It's not n, it's not the number of nodes times the degree, it's n squared. So, okay, the Google people were scratching their head and saying, how do we implement this 10 billion by 10 billion matrix? Can you even store it in memory? How much memory would you need for that matrix? A lot, huh? Can you store it in memory? What do you think? Is there a system, even today, that could store a matrix like that? No, huh? I mean, 10 billion by 10 billion, that's 10 to the 20th elements. Even Google today doesn't have like that kind of storage, okay? So the fix is you have to be smart, as usual. Question?
The universe doesn't contain enough atoms to store the geometry?
It might, sure. There's probably, if you had a computer the size of the Earth, you could store it. Because sometimes physicists say there's 10 to the 76 particles in the universe. So yeah, you're fine. If you have the universe, you can store it.
Okay.
But I don't have the universe in my pocket, so I can't store it. So the idea is to be a little bit smart. The idea is not to add the teleportation to every single number, but to kind of keep it separate. Okay? So So here you have this is the computation you're doing. Huh? You have some vector, you multiply by PageRank, and you're basically looking for eigenvalue convergence of this thing. Huh? But you don't want to store this matrix, it's too big. So what you do is you keep this one, the original one, which does not have which has lots of zeros, does not have the teleportation, and the teleportation is added only after that. So this is like a tax, okay? It's basically, because it's always the same for every node, it doesn't depend on the node, that means you can add it in separately, okay? So this is like 1 minus beta over n. And so that way you don't actually have to store 10 to the 20 elements. The matrix is sparse, okay? This matrix, the number of elements is basically similar to the number of edges, okay? And so it's much, much less, okay? M is what's called a sparse matrix. So most of the entries in the M are zeros. You can implement it much more efficiently, okay? Okay, of course you have to handle the dead ends, okay? Be careful with the dead ends, because you have to jump out. For the dead ends, it's not 1 minus beta, you have to be careful, because you need to jump out 1 over n for the dead ends, huh? Okay, and then you get something nice. So you get this nice figure. Each of the nodes here is proportional to the PageRank, so B and C are very important. And E is not so important, and so on. Okay. Okay, so that's the basic PageRank. But once people invent PageRank, there's actually lots of extras that people want to do. So there's still kind of problems, and we'll talk about some of them. The first thing is that PageRank measures the popularity in general of the page. How popular is the page? But maybe I'm only interested in stamp collecting, and I want to know what is the best page for stamp collecting, and I'm not interested in a general popularity. Because maybe there's not so many people doing stamp collecting, and there's many more people interested in Kalashnikov machine guns than stamps, so there would be no, the stamp pages would have much less popularity. So you want maybe a PageRank that knows about topics. Okay, so we'll explain that a little bit. And another thing is you can take this, you can also use PageRank to find similarities. That's important. If for example, if I'm looking for pictures, I'm looking for pictures of trees, for example, and I have this very nice palm tree, and I want similar pictures. You can use a similar algorithm than this to find similar pages. So that's nice. Okay, that's one thing. That's making it very specific. Another problem is spam. Okay, it's possible to spam or to cheat on the PageRank, and this is called web spanning, and you can do things like link farms, and there's a way around that. You have to somehow know what are trusted pages. So there's an algorithm called TrustRank. And finally, the hubs and authorities, there's two kinds of importance. Huh? There's the pages that are important, but also the pages that link to important pages. So PageRank only has one measure. Okay, so that we saw last time. But I'm going to talk about these two, topic-specific and web spamming. So beyond PageRank, first topic-specific. So I have some graph here with the heavy nodes and the heavy links and the light links. But I'm interested in some kind of topic. So I want only to look at the good pages in a particular topic. So how do I do that? I have to give more influence to pages that are close to some topic. And the way to fix that is you change how you teleport. Instead of teleporting to any random page, you teleport to pages that are kind of relevant, okay, that have something to do with sports or stamp collecting. Okay? And once you know that, you have the teleport set, you change the teleport set, you can still use the regular PageRank. So that works really well, the topic-specific element. Okay. Okay. How do we get this teleport set? Well, there's different ways. You can use classic techniques from older search engines. You can look at the content of the pages for that. Okay. You could also look at who is making the query. Okay. You can look at browsing history. Okay. If I'm type Manchester, what do I mean? Do I mean football team, or do I mean the city, Manchester? Well, it depends on my browsing history, maybe. Okay, so there's many ways to do that kind of stuff. Okay, and that's how topic-specific works. Another way you can extend PageRank is measuring similarity or proximity. So here's an example. Let's say we have this graph here. Look at these two nodes, 1 and 4. How close are they in some sense? Or 7 and 1. How close is it? Because the shortest path is the same. 1, 2. But maybe 4 is closer because there's more paths. Maybe 4 is closer to 1 than 7. Because 7, there's only one path. Okay? Multiple 2-hop paths. But only one path from 1 to 7. Okay? So that's one way of extending it. So this is called SimRank. So here's another example. I have 4 pictures, and I want to show how similar are these pictures. So picture 1 has a house and a tree. Picture 2 has a house and a mountain. Picture 3 has a house and a tree. And 4 has a tree and a mountain. So which pictures are similar to picture 1? How similar is picture 1 to 4? Okay. Or maybe there's ones that are closer. 1 to 3 might be closer because they're both having a house and a tree. So we can use something like PageRank to figure that out. Okay. So this is kind of like topic specific. Again, we want to bias the teleport set and recalculate the PageRank. So it's a kind of variation on PageRank. So the idea is that the teleport set is the node itself. So the node is closest to itself. Okay. Usually the teleport set is all relevant nodes, but here the node is the one closest to itself. Okay. So that's one way that you modify the PageRank. You make random walks from a fixed node, okay? And then you can do things like, here's an example with authors, conferences, and tags. So articles, authors, people writing articles on this. So this you do it for all nodes. This is actually used in a website called Pinterest. You may be using it for recommendation. They use something like this. Okay? So this is also known as PageRank with restarts. So here's the example with the pictures. So what is the most related picture to picture 1? Okay, you have your teleport set, which is picture 1, and you do your random walks with the restart, and the result of this is going to be picture 3. Okay, so if you look here you have your graph with 7 nodes. Here you have your transition matrix. Okay, and now you do the convergence of this. Okay, and you can see. Notice you have 2 groups. You have the picks, the four picks on the top, and the 3 attributes on the bottom. Okay, so you compute the PageRank matrix, and you can see that here you can do the restart. Okay, on pick 1. So from pick 1, you go 1, 2, 3, 4. It's like a teleport. And here you have the three things on the bottom, okay? And the result is that pick 1 and pick 3 are going to be the closest when you converge this, okay? That's one way of extending PageRank. And in this other example, when I had node 1, you can see that 1 and 4 are pretty close, 0.24, but node 7 is farther away, it's 0.07. Okay? So basically doing the PageRank with the restart. Okay? So that gives us three kind of variations of PageRank. The normal PageRank, which teleports randomly. We have the topic-specific PageRank, which teleports to pages that are relevant, and we have the SimRank, which always teleports to the same node for finding similar nodes. So these are three different ways of using PageRank. Okay. So now, the final thing I want to say is web spamming. How do you can cheat on PageRank, okay? What is web spamming? So web spamming is a deliberate action to boost a web page in ranking. And there's lots of these there's lots of spam pages, okay, which are created only to appear in your rank results that should not be there. So this thing, like I mentioned before, has a very dignified name called search engine optimization, but it's basically cheating. So Google has spent a lot of effort combating this. So let me talk a little bit about cheating. How do you cheat on the web? In the early search engines, how did they work? So they crawl the web, they look at all the pages, they index the pages, and they respond to queries so there are pages containing words. That's in the olden days, that's before PageRank, okay? That's very easy to cheat there. How do you measure the importance? Well, in the early search engines, you look at how many times the words are there, or what is the header. If the header words, okay. So of course it's very easy to cheat if you do that. So as people began to use search engines, there were companies that tried to exploit it to cheat. So here's an example. So I'm selling shirts, and I want lots of people to come to my website. So I want to pretend that my website is about movies. So how do I do that? Well, I use a technique. For the early search engines, it was pretty easy. Okay? How do I make my page appear to be about movies? It's very easy. I add the word movie 1,000 times to my page, but I make it so it's white so that nobody sees it, and search engines will see it. Yeah?
And can you also spam on the importance of your page?
Yeah. This is before PageRank, yeah? So this doesn't work anymore now. I'm giving it for history. But there's also a way to spam PageRank, which I explain in a few minutes, which is called link farms. Okay? Another way is you run the query movie, you see what is the page that came first. So that's an important page, and you take the text of that page and you just copy it into yours. Cheat. This is called term spam. Okay? So Google made a solution to that. Instead of using the words in the page, you use the words in the link to the page, which is called the anchor text, and the surrounding text. So what people say about you. And of course, you use PageRank to measure the importance. So with PageRank, the shirt seller doesn't work. His technique doesn't work anymore. It doesn't matter if the short seller puts the word movies in his pages, because no movie pages are going to link to this page, okay? So he's not going to be ranked high for movies, or even for shirts. But you can cheat on this, and this is called link farms, okay? Okay, so let's say the shirt seller, he creates 1,000 pages. Each of those pages links to the movie page. Okay, yeah. But those pages have no inlinks. That doesn't really work, huh? Even if he picks a million pages pointing to the shirt page, real important movie pages like IMDb, there's no way he can beat them. Okay? But there is a way to beat PageRank. We spam farming, kind of coordinated with that. And this has been used, and it's sometimes called Google bombing. A few years ago, now it works too. If when George Bush was president, you type miserable failure in Google, it points to the biography of George Bush. It's nice, huh? Miserable failure links to Bush. And it's still done. It's called Google bombing. So how does that work? It's possible to do that, to cheat. This is called spam farming. It's possible to create a structure in the graph that concentrates the page rank of a particular page. Okay, how does that work? So I'll show you the technique. So basically it works like this. There's three kinds of pages. So let's say I'm a spammer. I want to cheat. Okay, I want to increase the page rank of some page. So I look at the web, and there's three kinds of pages from my point of view. There's inaccessible pages. That's pages owned by other people. Most of them are inaccessible. Then there's accessible pages. These are pages owned by other people, but I can add something to them. Blogs, for example, or comments, reviews. I can post there. So I can put something there, even though I'm not the owner. It's called accessible pages. And finally, there's a small number of pages that are owned by me, the spammer. These are called owned pages. So I have these three kinds of pages. So how can I use this? So that's the structure. So here's the web. This is the whole web. And here's the page, and I want to increase the page rank of this one. So how do I do it? Okay. I want to maximize the page rank of T. The web has two kinds of pages. So the green ones, those are the ones that I can add something to, even though I'm not the owner, like their blogs, or I can put a comment or something, okay? Then the others are inaccessible. I have no control over them. Most of them are inaccessible. Huh? You might have a few pages where you can add, but most of them are owned by other people. So I can't do anything there. Fine. So what do? Well, the first thing I do is I post on as many places as I can links to T. I link to T from as many accessible pages as possible. That's the first step. It's not enough, but it's the first step. That will already increase a little bit the page rank of T. But that's not enough. What I really have to do then is I do another step where I construct what's called a link farm to multiply the page rank of T. So these red pages are my pages. So I buy a bunch of machines, or I rent machines, and I can write anything I want on them. And this is my link farm, all these red pages. And the link farm pages will all point to T. And T points back to them. So this seems kind of weird, huh? All these pages are going to point to T, and on T I make a link back from them. And that's called the link farm. And these red pages are owned by me. Okay? So how does this work? So this will actually improve my page rank. Notice there can be many here, millions, but not billions. But there could be millions. So how can this work? So let's make some computations. Let's compute the page rank now. So let's say there's n pages that are inaccessible. N is huge number. and there's m pages that are owned by me, okay? Which is also a big number, but much smaller than n. Okay? Let's say that little x in green is the page rank that comes from the accessible pages. Okay? It's not so big, but there's some numbers. And y is the page rank of page t. Now we can compute, according to PageRank, what it's going to be. So first of all, what is the rank of one of these pages? What is the rank? So there's several sources of rank. One source comes from the outlet of T, but another one comes from the teleportation. Okay? So it's like this. So each form page has this rank. So y is the rank of theta, so it's beta y over m plus 1 minus beta over n. See that? So it's the page rank coming from T and the teleportation rank. Okay? Okay, let's go on. So what is the rank of page T? Well, it's the page rank coming from the green pages plus all the page rank. These only have one outlink, and they're all going to T. So it's m times beta, and this is the page rank coming from the red pages. Beta y over m plus 1 minus beta over n. You also have teleportation to page T. So this is a very small number. Okay, so here we have a nice formula. So let's simplify this and see what we can learn from it. Okay, so we can simplify this a little bit. So this y is equal to x plus beta squared y plus this beta times 1 minus beta over m times m over n plus this very small number. Okay, this number we can remove, it's too small. And then we simplify. We have y on both sides here. So it's 1 minus beta squared. So y is equal to x divided by 1 minus beta squared plus this number divided by 1 minus beta squared. So it's some constant times m over n. So what does that mean? Okay, so the value of the constant is beta over 1 plus beta. Okay? What can we learn from this? What can we learn from this? How can we increase now the page rank of y? Notice there's this m factor here. By making n large, we can make y as large as we want. So independent of everybody else. If we put 1,000,000 pages here, we make it large. If we put 10 million, it's much bigger. You add a number proportional to m. So that means the more pages you put in the farm, the higher the page rank gets. Okay? And that's how these link farms work. So how can that work? What is really the idea here? How is this working? Well, it's because these farm pages, they all get teleportation is going to them. And the more you have of them, the bigger fraction of teleportations will go there. So the teleportation, here, 1 minus beta over n times m. So it depends on the fraction of m over n. The bigger that m is, the more that teleportation will go there, and the more you can increase the page rank. And it doesn't matter what anybody else does. They do whatever they want. If I'm rich enough, I just have to create a lot of pages, and the teleportation will go there, and I can increase that. So the search engine optimizers, this is what they do. Okay? The random teleportation from all the web to the farm nodes gets concentrated and pushed into page T. Okay? And this is how the link farms work. Okay? Actually, you might say, yeah, but M is still going to be very small compared to N. This is true. But you don't have to have M be large compared to N. It just has to be larger than your competitors. So if you're a shirt seller, as long as you get higher up than other shirt sellers, you're good. You're not competing with really popular pages like Amazon or so on. You're only competing with other shirt sellers. So M doesn't even have to be that large. But of course, the shirt sellers will all be paying these companies, the search engine optimizers, for increasing their rank. And the one who pays the most will increase the rank the most. Okay. So this was a big problem for Google in the early days. They have now fixed sort of that problem. So a lot of the problem, you see how it works, huh? So a lot of the problem of this has been fixed now. This was a big problem in the first decade of the 2000s. Really big problem. But so Google spent a lot of effort to try to fix this. So the algorithm they use now is a secret. Nobody knows what it is. Okay? And does it fix the problem? I don't know. What do you think? Is there still people doing search engine optimization?
Yes.
They still do it?
Yeah.
That means Google is not that successful, right? But here's an idea how to fix it. This is called trust rank, and it's based on a concept of what's called spam mass. So we want to combat this. So this is called link spam. Okay? How do you combat this? Well, one way is that you know where the spam farms are, and you blacklist them, but of course they're not going to announce themselves publicly, okay? So that doesn't always work. But the other way would be teleporting only to trusted pages. Right? This one here, you're teleporting to all these pages, even the farm pages, but maybe they're not trusted. So somehow you have to find out what are trusted pages, and you teleport mostly to them. Okay? And the idea is it's very rare for a good page, a non-cheating page, to point to a spam page. These spam pages tend to be hidden inside link farms, okay? So you change your teleport set, again, to be not everybody, but trusted pages. So it's a variation of topic-specific PageRank, okay? So you do a trust computation. You start from trusted pages, and you compute trust. And you split trust across the outline, links, and the degree of trust. So you have some pages trusted, whatever, New York Times, trusted page. The degree of trust decreases with the distance. So there's some way of distributing trust, okay? So this is not that easy, because you can't actually inspect all the pages manually. You want to have a lot of pages that are trusted. The more, the better. But you have to make sure they're trusted. So how do you do that? Well, one way is to use PageRank itself. Usually, the top pages produced by PageRank are okay, because the link farms, they can't actually push the page up so high. Or you have certain domains where you know that it's trusted. The .edu domain is universities, for example, or .gov government pages are trusted, for example. Okay, and all pages below the threshold are marked as spam. But that's still not really good enough. So the way that it's done in the trust rank model is we have this concept called spam mass. So you start with this green trusted set of pages, And you want to say, and this is the page you're looking at. And then you're looking at the page rank of this page. And you want to say, how much of this page rank is coming from spam, and how much is coming from trusted pages? Okay? So there's some kind of estimate. We don't really know. So RP is the page rank of page P. RP plus is the page rank of P when you teleport into trusted pages only. And then RP minus is the difference between the two. And this is called the spam mass. How much of the page rank comes from spam pages? Okay? What fraction of the page rank is coming from spam pages? So pages with high spam mass are spam. You throw them out. Okay? So even pages that are not in the trusted set, you can keep them if they have low spam mass. Okay? So this kind of idea, you have to do this if you want to not be killed by big farms. Okay? So this is one approach. The question, what is Google doing today? It's not really known, except for some people working at Google. Okay, it's kind of a secret. And that helps them, of course, because it's harder to cheat if you don't know the algorithm. Okay, so let me now just summarize the PageRank. PageRank is one of many powerful techniques. It's a kind of random walk. So we looked how that works. We represented it with matrices. So it's the concept of eigenvalue and eigenvectors can help us, okay, for understanding it. I showed a little bit the history. And then the problems. The matrices are very big. So how do you handle huge matrices? How do you handle topic specific? So there's a narrowing to topic specific, teleport to specific topics. You can also use it for finding similar nodes. And you can spam it. So I showed you how link farms work. They can increase the page rank, but you can combat that using algorithms such as TrustRank to estimate the spam mass, and so the link farms won't kill you. Okay, so let me end there. So that gives you some idea of all of the stuff going on around the PageRank. So of course the PageRank is very important. It was a key invention. It's what made Google rich and big. And the step after that was the advertising, the targeted advertising with the generalized second price. So that and PageRank is what Google made their empire out of. Okay, so let me stop there for today.